I wanted to solve another problem that involves stress and strain and elasticity. Again, it's a problem where we built a cable out of two wires. In the previous problem, we built the cable out of two wires in series. In this problem, we're going to build the cable out of two wires in what we call parallel. So we're imagining a situation where we got two wires of equal length. They're of equal area, cross-sectional area. They're different materials, and we arrange them in parallel, next to one another like this, adjacent to one another like this. And we're going to compute again the effective Young's modulus, the effective elasticity of the cable arrangement in terms of the individual elasticities of Young's moduli of the wires that make up the cable. Let me draw a picture of the situation. So here's a sketch of the arrangement of the two wires, a blue wire on the left, a red wire on the right, and some mass that's causing a stress on the two wires. Let's imagine that the length of the wire on the left is L. The cross-sectional area of the wire on the left is A. And the Young modulus of the wire on the left is Y1. And then correspondingly, the length of the wire on the right is L, the cross-sectional area of the wire on the right is A, and its Young's modulus is Y2. And we're interested in the Young's modulus, the effective Young's modulus, I'll call it Y, of this arrangement, this parallel arrangement. Parallel because they're next to one another, parallel because they're neighbors to one another, of the two wires. Well, we're going to solve this situation again with our master equation relating stress, strain, and elasticity, that the elasticity is the stress over the strain, where the stress is what you do to the cable, and the strain is the resulting elongation of the cable. So specifically, the stress on the cable is the force acting on it divided by the cross-sectional area of the cable, and the strain on the cable is the elongation divided by the length of the cable. I'm going to write down two formulas about the elongation of the cable and the forces that are creating the elongation of the cable. So the first one is that in this parallel situation, where the two wires are next to one another, adjacent to one another, the elongation of the entire cable, delta L, is the same as the elongation of wire number 1 on the left and wire number 2 on the right. So here, delta L, the elongation of cable, is just equal to delta L1, which is equal to delta L2. What about the forces in this arrangement? Well, there's some total force that's acting on the cable due to the mass that we've hung from the cable. I'll just call that total force F. That force is shared between the left-hand wire and the right-hand wire, so that there's a force, I'll call it F1 on the left-hand wire, a force F2 on the right-hand wire, and together they produce the total force that's exerted on the cable. And so that idea is that the total force on the cable is the sum of the individual forces on the individual wires that make up the cable. Okay, so I'm going to take this understanding of the situation, and again, I'm going to fill in the relationship between stress, strain, and elasticity into this understanding. And I'm going to work with the force equation here. So I can rewrite the force on the left-hand wire, that's F1, in terms of its Young's modulus and area and length and elongation. So if I substitute for the force on the left-hand cable in terms of the area of the cable, the length of the cable, the elongation of the cable, and the Young's modulus of the cable, I'm going to get the following. That force is equal to, equivalent to the Young's modulus multiplied by the cross-sectional area, multiplied by the elongation divided by the length of that cable. If I substitute for the second force on the right-hand cable in terms of the Young's modulus, the area and length of and elongation of the cable, I get the following. And finally, if I substitute for the total force that's acting on the entire cable made of the two wires in terms of the effective Young's modulus of that cable and its area, its length, its elongation, I get the following. Y is the effective Young's modulus. 2A is the cross-sectional area of the entire cable. Delta L is its elongation, and L is its length. Now, if you stand back and look at this formula that we've made, there's a lot of things that cancel. So, for example, in the denominator, the lengths cancel out. In the numerator, the elongations cancel out. And also in the numerator, the areas cancel out. There's A is the area of cable 1, A is the area of Y1, A is the area of Y2, and 2A is the area of the entire cable. And we're left with a relationship that 2Y, 2 times the effective Young's modulus of the cable, is the sum of the Young's moduli of the individual cables. And so that's the relationship between the individual Young's moduli, the two cables with the two wires with the two different materials, and the effective Young's modulus of the entire cable. Again, it's often useful to stand back from that equation and think whether that equation makes sense to us. And one way to check that it made sense was supposing the two parallel wires are actually the same material. So Y1 and Y2 are the same material. So Y1 and Y2 are the same Y. And then the equation just says that 2Y equals Y1 plus Y2, which is 2Y, i.e. the effective Young's modulus of the cable is the same as the Young's modulus of the two materials if the two materials are the same. So that makes a lot of sense. Also, if one cable had a much bigger Young's modulus and one wire had a much bigger Young's modulus and one wire had a much smaller Young's modulus, the Young's modulus of the cable as a whole is going to be determined by the Young's modulus of the stronger material. The stronger material takes over. The stronger material takes over and handles most of the stress. The stronger material takes over and handles most of the load.